Think about your life right now. You probably woke up to an alarm on your phone. You turned on lights. Maybe you made coffee with an electric machine. You're watching this video on a device powered by electricity. Every single thing you do, every moment of your day involves electricity in some way. But here's what's crazy. Just a few hundred years ago, nobody understood what electricity even was. Nobody could explain it, and nobody had any idea that this invisible force would completely change everything about how humans live. So how did we go from not knowing anything about electricity to building our entire world around it? That's what we're going to talk about. I'm going to tell you the real story, the actual journey of how humans figured this out. Because it wasn't one person who discovered electricity. It wasn't one moment. It was hundreds of years of people asking questions, making mistakes, and slowly piecing together this puzzle. Let's start at the very beginning. Way back in ancient times, people noticed something weird. If you rubbed certain materials together, strange things would happen. The ancient Greeks, around 600 years before the Common Era, they noticed that if you took amber, which is this yellowish hardened tree sap, and you rubbed it with fur or cloth, something magical seemed to happen. After rubbing it, the amber could attract light things like feathers or small pieces of straw. It was like the amber had some kind of power. Now, they had no idea what was causing this. They just knew it happened. They called amber electron in their language, which is actually where we get the word electricity from. But they couldn't explain it. They couldn't control it. They just knew that rubbing things sometimes created this attractive force, and for almost 2,000 years, that's basically where things stayed. People knew about this rubbing effect, but nobody understood it. Nobody was really studying it seriously. Fast forward to around the 1600s. This is when things start to get interesting. There's a man in England named William Gilbert. He's the personal doctor to Queen Elizabeth I, but he's also really curious about science, and he starts doing experiments with this rubbing effect that the Greeks had noticed. Gilbert doesn't just rub amber and call it a day. He tries rubbing all kinds of different materials. He rubs glass. He rubs sulfur, he rubs different types of stones and metals, and he discovers something important. It's not just amber that can attract things after being rubbed. Lots of different materials can do this, so he writes a book about it, and he uses the Latin word for amber, which is electricus, to describe this attractive force. He's basically saying, hey, this is a type of force, and we should call it electric force. This is huge because for the first time, someone is treating this as something that can be studied, something that follows rules. Gilbert is saying this isn't magic. This is something natural that we can understand if we investigate it properly. He creates the word electricity, and now other people start paying attention. But here's the thing. Gilbert and the people after him, they still don't really understand what's happening. They can see the effects, but they don't know what's causing them. They don't know that everything is made of tiny particles. They don't know about atoms. They don't know about electrons. They're basically trying to solve a puzzle without having all the pieces. So let's jump ahead a little bit to the early 1700s. There's this Englishman named Stephen Gray. He's not a famous scientist, he's not wealthy. He's just a guy who loves doing experiments, and Gray starts asking a question that nobody really asked before. He's wondering, okay, we know you can make things electric by rubbing them, but can that electric force move from one object to another? Can you transfer it? So he starts doing experiments. He takes a glass tube, rubs it to make it electric, and then he touches it to other things. Cork, metal, wood, different materials. And he discovers something amazing. The electric force can move. If he touches the rubbed glass tube to a long piece of string, the electric effect travels down the string. He can make it travel several hundred feet. He's found that electricity can flow from one place to another. But Gray notices something else too. It doesn't flow through everything equally. Some materials let the electric force pass through really easily. Other materials seem to block it or slow it. He doesn't have the words for it yet, but he's discovered the difference between conductors and insulators. Materials that let electricity flow and materials that don't. This is massive because now we're not just saying electricity exists. We're saying it's something that can move, something that can travel. And if it can travel, maybe we can control where it goes. Maybe we can use it. Around the same time, in France, there's a guy named Charles Dufay. He's also doing experiments with electricity, and Dufay finds something really strange. Sometimes when you rub two objects and make them electric, they attract each other. But other times, They push away from each other. They repel. This doesn't make sense at first. If electricity is just one thing, one force, how can it sometimes pull things together and sometimes push them apart? Dufay does more experiments and comes up with an idea. Maybe there are two types of electricity. He calls them vitreous electricity and resinous electricity. One comes from rubbing glass, the other from rubbing resin. And he notices that objects with the same type of electricity push each other away, but objects with different types attract each other. Now he's not exactly right about how this works, but he's identified something real. There is a positive and negative aspect to electricity, and they interact with each other in specific ways. This is another piece of the puzzle falling into place. Okay, so by the mid-1700s, people are doing all kinds of electricity experiments. It's becoming popular. Rich people in Europe are having parties where they demonstrate electric effects. It's like entertainment, but it's also serious science. People are trying to figure out the rules. What makes electricity? How does it move? What can we do with it? And this is when someone builds a really important tool. Actually, several people build versions of it around the same time. It's called a Leyden jar. Imagine a glass jar covered partly with metal on the inside and outside. The idea is that you can collect and store electricity in this jar. Before the Leyden jar, you could only use electricity right when you created it by rubbing things. Now, you could charge up this jar and keep the electricity stored in it. You could move it around. You could use it later. People go crazy for Leyden jars. Scientists start doing wild experiments with them. They connect multiple jars together to store more electricity. They touch the jars and get huge shocks. There are demonstrations where they send electricity through chains of people holding hands, and everyone feels the shock at the same time. This is when people really start to understand that electricity is powerful. It's not just a party trick. There's real energy here, and this brings us to one of the most famous names in the story, Benjamin Franklin. You probably know him as one of the founding fathers of America, but Franklin was also a serious scientist, and he becomes obsessed with electricity in the 1740s. He does experiment after experiment trying to understand how it works. Franklin comes up with a new way of thinking about electricity. Instead of two different types like Dufay said, Franklin thinks there's just one electric fluid, and objects can have too much of it or too little of it. He's the one who starts using the words positive and negative. If something has extra electric fluid, it's positive. If it's missing some, it's negative. And opposite charges attract, while same charges repel. Now Franklin is wrong about the fluid part. Electricity isn't actually a fluid flowing around them, but his positive and negative idea is basically correct, and we still use those terms today. This is a great example of how science works. You don't have to be completely right to make progress. You just have to be more right than the last person, and then someone else comes along and gets even closer to the truth. But Franklin's most famous experiment is the one everyone knows about, the kite and the lightning. In 1752, Franklin has this idea. He's been watching lightning storms, and he's thinking, you know what? Lightning looks a lot like the electric sparks we make in our experiments, just way bigger. Oh, what if lightning is actually electricity? What if storms are full of electricity? So he decides to test this. On a stormy day in June, he flies a kite with a metal wire attached to it. At the bottom of the kite string, he ties a metal key. The idea is that if lightning is electricity, and if his kite gets close to a storm cloud, the electricity might flow down the wet string to the key. He makes sure to stand under a shelter and keeps the string dry where he's holding it because he's not trying to get himself killed. And it works. He sees electric sparks jumping from the key. He can feel the electricity. He's proven that lightning is the same thing as the electricity they've been studying in labs. This is enormous because lightning is everywhere. It's powerful. It's part of nature. Now Franklin has shown that this natural phenomenon and the experiments scientists do are all the same thing. Electricity isn't just a human curiosity. It's a fundamental part of how the world works. Franklin's experiment is actually pretty dangerous. Some people who tried to copy it died because they weren't careful, but it leads to something really practical. Franklin invents the lightning rod. It's a metal rod you put on top of buildings. If lightning strikes, the electricity flows through the rod into the ground instead of through the building. This saves countless buildings from fire and destruction. One of the first practical uses of understanding electricity. But even with all this progress, people still don't really understand what electricity is made of. They can see its effects. They can move it around. They can store it, but they don't know why it works. What is electricity actually made of? What's happening on a deeper level? Let's move forward to around 1800. There's an Italian scientist named Alessandro Volta. Volta has been reading about experiments by another Italian named Luigi Galvani. Galvani had discovered that if you touch a dead frog's legs with two different metals at the same time, the legs twitch like they're alive. Galvani thought this was animal electricity, some kind of life force in the frog. But Volta thinks differently. He thinks the electricity isn't coming from the frog at all, it's coming from the metals. The frog is just reacting to it. Volta starts experimenting with different metals. He stacks them up in a specific way. He puts zinc and copper discs in a pile with pieces of cloth soaked in salt water between them. And something amazing happens. This pile of metals creates a steady flow of electricity, not just a quick spark like you get from rubbing things or from a Leyden jar, but continuous electricity that keeps flowing as long as the metals and salt water are in contact. Volta has just invented the battery. He calls it a voltaic pile, but we know it as the first electric battery. This changes everything. For the first time, people have a reliable source of electricity. They don't have to rub things. They don't have to wait for storms. They can just use a battery and get electricity whenever they want. Scientists all over Europe start getting their hands on voltaic piles. They start doing experiments that were impossible before because now they have a steady supply of electricity. With batteries, scientists discover they can do amazing things. If you put two wires from a battery into water, the water splits apart into two gases. They're using electricity to break apart water. If you connect a battery to certain metals dissolved in water, the metal comes out of the water and deposits onto the wire. This is called electroplating, and it becomes a huge industry. People start coating objects with gold and silver using electricity. Now we're in the early 1800s, and electricity is becoming really useful. But scientists also notice something strange. There seems to be a connection between electricity and magnetism. Magnets have been known about for thousands of years. They attract iron. Compasses work because of magnetism. Oh, but nobody thought magnets and electricity had anything to do with each other. They seemed like completely different things. Then in 1820, a Danish scientist named Hans Christian Ørsted is doing a demonstration for students. He has a battery connected to a wire, and there's a compass nearby. When he connects the battery and electricity flows through the wire, something unexpected happens. The compass needle moves, points toward the wire instead of north. When he turns off the electricity, the compass goes back to pointing north. Ørsted realizes what he's seeing. Okay, electricity flowing through a wire creates magnetism. These two forces that everyone thought were separate are actually connected. If you have electricity moving, you create a magnetic field around the wire. This is electromagnetism, and it's a huge discovery. Other scientists immediately start building on this. A French scientist named André-Marie Ampère does experiments and figures out the rules for how electricity and magnetism affect each other. He shows that two wires with electricity flowing through them will push or pull on each other because of their magnetic fields. These aren't just interesting effects. These are fundamental laws of nature that people are uncovering. Then in 1831, an English scientist named Michael Faraday makes another breakthrough. Faraday isn't from a wealthy family. He doesn't have a university education. He started as an apprentice to a bookbinder. But he's brilliant and curious, and he gets a job as an assistant to a famous scientist. He works his way up and starts doing his own experiments. Faraday knows that electricity can create magnetism because of Ørsted's discovery, but he starts wondering, if electricity can make magnetism, can magnetism make electricity? Can it work in reverse? So he does an experiment. He takes a coil of wire and he moves a magnet in and out of the coil, and he discovers that when the magnet is moving, electricity flows through the wire. The magnet is still, no electricity. Movement is the key. This is called electromagnetic induction. Faraday has discovered that you can create electricity by moving magnets near wires. You don't need batteries. You don't need to rub things. You just need movement and magnets. This is the basic principle behind every electric generator ever built. Every power plant in the world uses this principle. You spin magnets near coils of wire and electricity flows. This is how we make almost all of our electricity today. Faraday makes other important discoveries. He comes up with the idea of electric and magnetic fields. Before Faraday, People thought electricity and magnetism acted directly on things across empty space. Like one magnet would just affect another magnet instantly across the distance. Faraday says no, there's something in between. There's a field that fills the space around electric charges and magnets, and that field is what carries the force. This field idea becomes central to how we understand electricity and magnetism. By the mid-1800s, electricity is being studied intensely all over the world. Scientists have gone from knowing almost nothing to understanding quite a lot. They know positive and negative charges attract and repel. They know electricity can flow through some materials but not others. They know how to make steady electricity with batteries. They know how to create electricity with magnets. They know electricity and magnetism are connected, but there's still a mystery. What is electricity actually made of? What's physically happening when electricity flows? To answer that, we need to talk about atoms, because electricity and atoms are deeply connected. In the late 1800s, scientists are starting to understand that everything is made of tiny particles called atoms. Different types of atoms make different elements like hydrogen, oxygen, carbon, gold, iron. But atoms themselves aren't the smallest things. In 1897, a British scientist named J.J. Thomson discovers something smaller than atoms. Thomson is doing experiments with something called a cathode ray tube. It's a glass tube with the air pumped out and metal plates inside connected to batteries. When electricity flows through it, a strange beam shoots from one side to the other. Scientists have been seeing this effect for a while but don't know what the beam is made of. Thomson does careful experiments and proves that the beam is made of tiny particles. These particles are incredibly small, much smaller than any atom, and they're negatively charged. Thomson has discovered the electron. These electrons are parts of atoms. Every atom has electrons, and when electricity flows through a wire, what's actually happening is that electrons are moving from atom to atom. This is the answer to what electricity really is. Electricity is the movement of electrons. When you rub a balloon and stick it to a wall, you're moving electrons from one surface to the other. When lightning strikes, electrons are jumping from clouds to the ground. When you turn on a light, electrons are flowing through the wires and the filament. Everything about electricity comes down to the movement of these tiny, negatively charged particles. Thomson's discovery helps explain so many things. Why do some materials conduct electricity and others don't? Because in conductors like metals, the electrons can move freely from atom to atom. In insulators like rubber or plastic, the electrons are stuck and can't move easily. Why do positive and negative charges attract? Because one has extra electrons and one is missing electrons and they want to balance out. Why do batteries work? Because the chemical reactions inside move electrons from one side to another, creating a flow. With the discovery of electrons, the story of electricity comes full circle. It starts with ancient Greeks rubbing amber and seeing mysterious attractive forces. It goes through centuries of careful experiments by people like Gilbert, Gray, Franklin, Volta, Faraday, and many others. Each person adds a piece to the puzzle, and it ends with Thomson showing what's actually moving when electricity flows. The story doesn't stop there, because once people understand electricity, they start using it in ways that transform civilization. Let's talk about that. In the late 1800s and early 1900s, people start figuring out how to use electricity for practical things, not just in labs, but in homes and businesses and cities. One of the biggest applications is lighting. For thousands of years, humans used fire for light. Candles, oil lamps, gas lamps. Fire is dangerous. It creates smoke. It can burn buildings down. But what else can you use? Then people start experimenting with electric light. The basic idea is simple. You run electricity through certain materials, they get hot and glow. Make a thin wire and run electricity through it, and it gets so hot it glows white. That's an incandescent light bulb. The problem is that the wire burns up quickly if there's air around it, so you need to put it in a glass bulb and pump out the air. Then it can glow for a long time without burning up. Lots of people work on electric light bulbs, but Thomas Edison is the one who really makes them practical. In 1879, Edison and his team figure out the right combination of materials and design. They test thousands of different types of wire filaments. They try different shapes, different ways of removing air from the bulb, and they get it working reliably. Edison's light bulbs can burn for hundreds of hours. He doesn't just invent the bulb. He builds power stations to generate electricity and wires to deliver it to buildings. He creates the whole system. Electric light is revolutionary. Suddenly you can have light at night without fire. Factories can run longer. People can read and work in the evening. Streets can be lit up safely. Cities change completely. Within a few decades, electric lights replace gas lamps and candles in most developed countries. It's hard to overstate how much this changes daily life. Before electric light, your life was limited by the sun. You woke when it got light and slept when it got dark. After electric light, you could choose your schedule. Another massive application is electric motors. Remember Faraday's discovery that moving magnets near wires creates electricity? Well, it works the other way too. If you send electricity through wires near magnets, the wires move. They push and pull against the magnets. If you arrange this cleverly, you can make something spin continuously. That's an electric motor. Electric motors are amazing because they turn electricity into motion. And motion is useful for so many things. You can use motors to run machines in factories, to pump water, to power trains and boats, eventually to drive cars. Motors are quiet compared to steam engines. They're clean, don't need coal or wood. You just give them electricity and they work. By the early 1900s, electricity is spreading everywhere. Homes start getting wired, first just for lights, but then for other things too. Electric fans, electric heating, eventually refrigerators, washing machines, vacuum cleaners. All the home appliances we take for granted now are only possible because of electricity. Cities build power plants. At first, these are small and only serve a few buildings. But they get bigger. They build huge generators based on Faraday's principle. They use falling water to spin the generators in hydroelectric plants. They burn coal or oil to make steam that spins turbines connected to generators. String wires across cities and eventually across entire countries. The electric grid is born. The electric grid is one of the most important inventions in history. It means you don't need your own generator. You don't need batteries. You just plug into the wall and electricity is there whenever you need it. Someone else is making it miles away and sending it to you through wires. This is only possible because of everything people discovered about electricity over the previous centuries. Let's talk about some other ways electricity changes things. Communication is huge. In the early 1800s, if you wanted to send a message to someone far away, you had to send a person with a letter, on foot or horse, or it could take weeks or months. Then people invent the telegraph. The telegraph uses electricity to send messages. You have a battery, a wire connecting two places, and a device that can turn the electricity on and off. At the other end, you have a device that detects when electricity is flowing. By turning electricity on and off in patterns, you can send coded messages. Samuel Morse develops a famous code for this in the 1830s. Short bursts and long bursts of electricity representing different letters. Morse code. Suddenly, you can send a message across a country in seconds. Companies string telegraph wires along railroad lines and across continents. In 1866, they lay a telegraph cable across the Atlantic Ocean on the bottom of the seafloor. Now you can send a message from America to Europe almost instantly. This changes everything about business, news, and coordination. After the telegraph comes the telephone. In the 1870s, Alexander Graham Bell and others figure out how to use electricity to transmit actual voices. Not just coded beeps, but your actual voice. You speak into a device that converts sound waves into electrical signals. Those signals travel through a wire. At the other end, another device converts the electrical signals back into sound waves. Now you can have a conversation with someone on the other side of the world in real time. Then comes radio. In the 1890s, people figure out that you don't need wires at all. You can send electrical signals through the air as electromagnetic waves. Guglielmo Marconi and others developed radio transmitters and receivers. Now you can broadcast messages and eventually music and voices to anyone with a radio receiver. No wires needed. This leads to radio stations and later to television and eventually to cell phones and Wi-Fi, all based on using electricity to create electromagnetic waves. Every type of communication we have now, every phone call, every text message, every video you watch, every website you visit, it all uses electricity in some form. Information is encoded as electrical signals or electromagnetic waves and sent around the world at the speed of light. What about computers? Computers are entirely dependent on electricity. The first computers in the 1940s used vacuum tubes, which are electrical components that can switch on and off very fast. Later, transistors replaced vacuum tubes. Transistors are even smaller electrical switches, and now we have computer chips with billions of tiny transistors, all of them using electricity to switch on and off millions or billions of times per second. Computers are just machines that control electricity in very precise ways. When you type on a keyboard, you're sending electrical signals. When the computer thinks, it's moving electrical signals through millions of switches. When the screen shows an image, it's using electricity to light up pixels. Everything a computer does is ultimately about controlling the flow of electrons. And this brings us to today. Look around your life. Your phone is a computer running on electricity. Your lights, your heating, your refrigerator, your stove, your car probably, your TV, your internet router, your watch. Almost everything is electric or has electrical components. Factories are full of electric machines. Hospitals use electric devices to monitor patients and perform surgeries. Airplanes have electrical systems controlling everything from engines to navigation. Cities are lit at night with electric lights. The entire economy runs on electricity now. If the power goes out for even a few hours, everything stops. We're using more electricity than ever because we keep finding new things to do with it. We're building electric cars to replace gasoline. We're using electricity to heat homes instead of burning gas. We're running massive data centers full of computers that store all the information on the internet. We're even looking at using electricity to capture carbon from the air to fight climate change. Scientists are still studying electricity. They've discovered things the early pioneers couldn't imagine. They know that electricity and magnetism are actually the same thing viewed from different perspectives. They know that light itself is an electromagnetic wave. They've developed quantum mechanics, which explains how electrons behave in atoms in ways that seem impossible but are experimentally proven. They're using electricity to do things like create powerful particle accelerators that smash atoms together to understand the fundamental building blocks of the universe. So let's think about this journey. It starts with someone in ancient Greece rubbing amber on fur and noticing it attracts feathers. That's all they know. Something weird happens when you rub things. For 2,000 years, that's basically all anyone knows. Then people start experimenting seriously. They find you can move electricity, store it, that there are positive and negative charges, that lightning is electricity, that you can make electricity with batteries, that electricity and magnetism are connected, that you can make electricity from motion. Each discovery builds on the last. Each person sees a little further because they're standing on the shoulders of everyone who came before. Then they discover what electricity actually is, the movement of electrons, and once they understand it, they use it to transform the world. To light cities, to power machines, to communicate instantly across any distance, to build computers, create the modern world we live in. This is how science works. You start with curiosity about something you observe. You do experiments. You form ideas about how it works. You test those ideas. Sometimes you're wrong and you try again. Sometimes you're partly right and someone else comes along and improves your idea. Slowly, piece by piece, you build up an understanding. And once you understand something, you can use it. The people who discovered electricity weren't doing it to make smartphones or computers or power grids. They were doing it because they were curious. They wanted to understand. They saw something interesting and they asked questions. How does this work? Why does it do that? What would happen if I tried this? And by asking those questions and doing experiments to find answers, they uncovered something fundamental about nature. And here's what's beautiful about this. Electricity was always there. It was always part of how the universe works. Electrons were always moving in atoms. Electromagnetic forces were always holding atoms together. Lightning was always striking. But for most of human history, we didn't know any of this. It was invisible to us. We lived surrounded by electricity without seeing it. Then people started paying attention. They started investigating, and they uncovered this hidden aspect of reality. They made the invisible visible. They took something we couldn't understand and turned it into something we could harness and use. That's the power of science and human curiosity. Think about what your life would be like without electricity. No lights at night. No refrigeration so food spoils quickly. No instant communication. No computers. No internet. No modern medicine because hospitals depend on electric equipment. No airplanes because they need electrical systems. No cars because modern cars are full of electronics. You'd be living essentially like people did in the 1700s or earlier. Your whole world would be confined to a small area because you couldn't travel far or communicate far. Your life expectancy would be shorter because medicine would be primitive. Everything we have, everything we can do, everything that makes modern life modern, it all traces back to people asking questions about electricity. People like Gilbert wondering what happens when you rub different materials. Franklin asking if lightning is electricity. Volta figuring out how to make a battery. Faraday discovering you can make electricity from motion. Thomson finding the electron. And thousands of others whose names we don't know but who contributed pieces to this puzzle. This is why science matters. This is why curiosity matters. This is why asking questions and doing careful experiments matters. Because sometimes when you investigate something that seems like just an interesting curiosity, like why amber attracts feathers after being rubbed, you end up discovering something that changes everything. Electricity was discovered through centuries of work by countless people, each one adding a small piece. Some pieces were big breakthroughs, some were small improvements, but they all mattered. They all contributed to the full picture. Now we live in a world that runs on electricity, a world that wouldn't be possible without all those discoveries. So the next time you flip a light switch or charge your phone or turn on your computer, remember that you're using something that people spent centuries figuring out, something that was once mysterious and unknown, something that people worked incredibly hard to understand. And remember that there are probably other mysteries out there right now, things we don't understand, that future people will look back on and wonder how we ever lived without them. Now let's dig deeper into some specific moments that really show how this discovery process worked, because understanding the details helps us appreciate just how difficult and amazing this journey was. Let's go back to Benjamin Franklin for a moment. When Franklin started his electrical experiments in the 1740s, he wasn't just doing random tests, he was systematic. He would set up experiments, write down exactly what happened, and try to find patterns. One thing he noticed was that electricity seemed to flow better through some shapes than others. He discovered that pointed objects, like needles or sharp tips, seemed to draw electricity more easily than round or flat surfaces. This observation led to the lightning rod design. Franklin reasoned that if you put a pointed metal rod on top of a building and connect it to the ground with a wire, the lightning would be attracted to the point. It would travel down the metal instead of through the building's wood and structure. This was genius because it was based on careful observation and logical thinking. He tested his lightning rods in Philadelphia, and they worked. Buildings with lightning rods didn't burn down during storms. Buildings without them did. But here's something interesting. When Franklin first proposed lightning rods, some people were against them. They thought it was wrong to interfere with lightning because they believed lightning was God's will. There were religious objections. Some people thought trying to control or redirect lightning was blasphemy, but Franklin kept promoting them because the evidence was clear. They saved lives and property. Eventually, lightning rods became standard on important buildings. This shows how scientific discoveries sometimes face resistance, not because the science is wrong, but because they challenge existing beliefs. Let's also talk more about Volta and the battery. When Volta invented the voltaic pile around 1800, he didn't just stack some metals together and call it a day. He experimented with different combinations. He tried copper and zinc, silver and zinc, iron and zinc. He tried different liquids between the metal discs, salt water, acid solutions, plain water. He was trying to find the combination that produced the strongest and most reliable electric current. What Volta discovered was that different metals produce different amounts of electricity. Some combinations work better than others, and the liquid between the metals matters too. Acids work better than plain water. This is because, although Volta didn't know it at the time, what's happening is a chemical reaction. The acid is reacting with the metals, and this chemical reaction moves the electrons from one metal to another. That flow of electrons is the electric current. Volta's battery was revolutionary because before this, the only ways to make electricity were temporary. You could rub things together and get a brief charge. You could build up charge in a Leyden jar, but once you used it, it was gone and you had to charge it up again. But Volta's pile kept producing electricity as long as the chemicals didn't run out. It was like having a steady stream instead of occasional buckets of water. Scientists immediately started using voltaic piles for new experiments. In England, two scientists named William Nicholson and Anthony Carlisle got their hands on a battery shortly after Volta announced his invention. They connected wires from the battery into a container of water, and they saw bubbles forming on the wires. When they collected these bubbles, they found two different gases. one was hydrogen. They had split water into its component parts using electricity. This process is called electrolysis. This was incredible for multiple reasons. First, it showed that electricity could drive chemical reactions. It wasn't just about sparks and shocks. You could use electricity to break apart or combine chemicals. Second, it proved that water wasn't an element. Water could be broken down into hydrogen and oxygen, which meant water was made of smaller components. This helped chemistry advance as a science. Other scientists used electricity for electrolysis. Humphrey Davy, a British scientist, used powerful batteries to isolate new elements. He discovered sodium and potassium by using electricity to break apart their compounds. Before this, nobody had seen pure sodium or potassium. They were locked up in combinations with other elements. Electricity gave scientists a tool to pry them apart. Now let's talk about Michael Faraday in more detail. Faraday's life story is pretty remarkable. He was born in 1791 to a poor family. His father was a blacksmith who struggled to support the family. Faraday had only the most basic education. At 14, he became an apprentice to a bookbinder. While binding books, he started reading them. Science books especially fascinated him. He attended public lectures on science whenever he could. In 1812, he went to lectures by Humphrey Davy, one of the most famous scientists in England. Faraday took detailed notes and later sent them to Davy along with a request for a job. Davy was impressed and hired Faraday as his assistant. This changed Faraday's life completely. Faraday worked for Davy for years, helping with experiments and learning constantly. Then he started doing his own research. In 1821, he built a device that used electricity to create continuous rotation. It was the first electric motor. He showed that electricity flowing through a wire in a magnetic field would cause the wire to spin around the magnet. This was proof that electrical energy could be converted to mechanical motion. But Faraday's greatest discovery came in 1831. For years, scientists knew that electricity could create magnetism. Thanks to Ørsted's discovery, Faraday became obsessed with the reverse question. If electricity makes magnetism, can magnetism make electricity? He tried many experiments. He wrapped coils of wire around iron rings. He placed magnets near wires. Nothing seemed to work. Then one day, he was moving a magnet into and out of a coil of wire. His equipment detected a brief pulse of electricity each time the magnet moved. When the magnet was still, nothing. When it moved, electricity flowed. The key was motion. Change. A stationary magnet near a wire did nothing, but a moving magnet created electricity in the wire. Faraday tested this with many variations. He spun magnets near coils. He moved coils near magnets. He changed the speed. He changed the strength of the magnets. And he found that the faster the motion and the stronger the magnet, the more electricity was created. He had discovered electromagnetic induction. This principle is the basis for every electric generator in existence. Think about what this means. Before Faraday, if you wanted electricity, you needed batteries. And batteries use up their chemicals and stop working. But with Faraday's discovery, you could make electricity from motion. And motion is everywhere. Falling water has motion. Wind has motion. Steam pushing a turbine has motion. You could hook up any moving thing to a generator and make electricity continuously. Power plants today still use this principle. In a hydroelectric plant, water falls from a high place and spins a turbine. That turbine is connected to magnets and coils. The magnets spin past the coils. Electricity is in a coal or natural gas power plant. Fuel is burned to heat water into steam. The steam pressure spins a turbine. That turbine spins magnets past coils, generating wind turbines work the same way. The wind spins the blades spin a generator, and out comes electricity. Even nuclear power plants use this principle. Nuclear reactions heat water into steam. Steam spins turbines spin generators. It's all Faraday's discovery. The only difference between power sources is what makes the magnets spin. But once they're spinning, the process is the same. Faraday also made other contributions. He invented the Faraday cage, a metal enclosure that blocks electrical fields. If you're inside a Faraday cage, electromagnetic waves from outside can't reach you. This is why you can be inside a car during a lightning storm and be safe. The metal car body acts as a Faraday cage. The electricity flows around the outside and into the ground, but not through the inside where you are. Faraday also introduced the concept of field lines. He visualized electric and magnetic fields as lines flowing through space. If you sprinkle iron filings near a magnet, they arrange themselves in patterns. Those patterns show the magnetic field lines. Faraday used this visualization to think about how forces spread through space. His field line concept became fundamental to physics. Later, James Clerk Maxwell would build on Faraday's ideas to create equations describing electromagnetism. Speaking of Maxwell, let's talk about him. In the 1860s, Maxwell was a Scottish physicist trying to understand electricity and magnetism mathematically. Faraday had discovered the phenomena and described them, but he wasn't a mathematician. Maxwell took Faraday's ideas and turned them into precise mathematical equations. Maxwell's equations describe how electric and magnetic fields interact and change. They show that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. They're linked together, constantly creating each other. When you have these fields creating each other, they form waves that move through space. Electromagnetic waves. Maxwell calculated the speed of these waves and found it matched the speed of light. This led him to a stunning conclusion. Light is an electromagnetic wave. Light isn't a separate phenomenon. It's electricity and magnetism oscillating together, traveling through space. This was a massive unification of physics. Optics, the study of light, and electromagnetism were now the same subject. Maxwell's equations also predicted that electromagnetic waves could exist at any frequency, not just the frequencies of visible light. There could be waves with longer wavelengths and lower frequencies, and waves with shorter wavelengths and higher frequencies. At the time, this was just a mathematical prediction. Later, people would discover radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. All electromagnetic waves, just at different frequencies. All predicted by Maxwell's equation. This is what theoretical physics does. You take experimental observations, create mathematical models, and those models predict new things that haven't been observed yet. Then people do experiments to test the predictions. If the predictions are right, you know you're understanding something deep about nature. Maxwell never lived to see many of his predictions proven, but they were, and his equations are still used today completely unchanged over 150 years later. Let's jump to the late 1800s and talk about Thomas Edison and the practical application of electricity. Edison wasn't the first person to invent an electric light. Many people had built versions before him, but Edison was the one who made electric lighting practical and commercially successful. How did he do this? First, Edison tested thousands of materials for the filament, the thin wire inside the bulb that glows. He tried platinum, which worked but was too expensive. He tried various types of carbon made from different plants and materials. He tried bamboo, which actually worked pretty well. His team tested material after material, keeping detailed records of what worked and what didn't. Eventually, they found combinations that could last hundreds of hours without burning out. But Edison knew that just inventing a light bulb wasn't enough. You also needed a whole system. You needed power plants to generate electricity. You needed wires to carry it to buildings. You needed meters to measure how much electricity each customer used. You needed switches and sockets. You needed trained workers who could install and maintain everything. Edison built all of this. In 1882, Edison opened the Pearl Street Power Station in New York City. It was one of the first commercial electric power plants. It had 6 generators based on Faraday's principle, driven by steam engines. Wires ran underground to nearby buildings. Customers could have electric lights installed in their homes and businesses. They paid based on how much electricity they used, measured by Edison's meters. First, only a few dozen buildings were connected. The system had problems. Wires overheated. Connections failed. Equipment broke down, but Edison and his team kept improving it. They figured out better insulation for wires, better designs for generators, better ways to measure usage. Within a few years, electric lighting was spreading through New York and other cities, but there was a big debate happening at the same time. Edison's system used direct current, or DC. This is electricity that flows in one direction, like from a battery. But there was another type of electricity called alternating current, or AC, where the flow reverses direction many times per second. Edison believed DC was safer and better, but others, particularly Nikola Tesla and George Westinghouse, argued that AC was superior for long-distance transmission. Here's why AC won. When you send electricity through a long wire, some energy is lost as heat. The amount of loss depends on the current, the amount of electricity flowing. Lower current means less loss. But people need a certain amount of power, which is voltage times current. So if you increase the voltage, you can decrease the current and still deliver the same power. Less current means less loss in the wires. With AC, you can easily change voltage using a device called a transformer. You can generate electricity at 1 voltage, increase it to very high voltage for transmission, then decrease it back down for use in homes. With DC, changing voltage is much harder. So AC systems could transmit power over many miles efficiently, while DC systems couldn't. There was a fierce competition between Edison's DC system and the AC systems promoted by Tesla and Westinghouse. This period was called the War of Currents. Edison tried to show that AC was dangerous, even going so far as to demonstrate AC killing animals to prove his point. But in the end, the technical advantages of AC won out. Most power grids today use AC for transmission, though some DC is used in certain situations. Nikola Tesla deserves special mention because he made many contributions to our understanding and use of electricity. Tesla invented the AC induction motor, which is widely used today. He worked on wireless transmission of power and information. He invented the Tesla coil, which can generate very high voltages. He held hundreds of patents and envisioned many technologies that wouldn't be built until decades after his death. Tesla was also known for dramatic demonstrations. He would use his Tesla coil to create enormous electrical sparks and arcs. He would light fluorescent bulbs just by holding them near electrical fields without any wires. He once lit up hundreds of lamps wirelessly to demonstrate the potential of his systems. These demonstrations captured public imagination and helped people see electricity as something powerful and almost magical. By the early 1900s, electricity was transforming society rapidly. Cities were getting wired, not just for lights, but for all kinds of applications. Electric streetcars replaced horse-drawn carriages in many cities. Factories installed electric motors to run machinery, replacing dangerous and dirty steam engines. Homes started getting electric appliances. The impact on daily life was enormous. Before electricity, people's days were governed by sunlight. You worked during the day and rested at night because you couldn't see well enough to do much else. With electric lights, you could work or read or socialize at night. This extended productive hours and changed sleep patterns. Some historians argue that electric lighting changed human society more than almost any other invention. Factories could now run night shifts. This increased production dramatically. Workers could work in well-lit conditions instead of dim, dangerous facilities. Electric motors made factories quieter and cleaner because there was no coal smoke or steam. This made factory work slightly less awful, though it was still hard and often dangerous. In homes, electricity slowly took over tasks that used to be done manually or with fire. Electric irons replaced flat irons heated on stoves. Electric washing machines replaced hand washing. Electric refrigerators replaced ice boxes that needed blocks of ice delivered regularly. Each appliance saved hours of labor, especially for women who did most household work at that time. This gradually contributed to social changes, though it took many decades. Let's talk about communication technologies more. The telegraph was revolutionary when it was invented. Before the telegraph, information could only travel as fast as a person or animal could carry it. A message from New York to California took weeks. With the telegraph, it took minutes. This changed business, journalism, and personal communication. Railroads particularly benefited from the telegraph. They could coordinate train schedules across long distances. They could warn of delays or problems. This made rail transport much safer and more efficient. Telegraph lines often ran alongside railroad tracks because it was convenient to string them on the same poles and because railroads needed telegraph communication to operate. The telegraph also changed how news worked. Before, newspapers printed local news because that's what they could get quickly. National or international news would be old by the time it arrived. The telegraph, newspapers could print current news from anywhere, and the wire services like the Associated Press developed to distribute news stories to many newspapers via telegraph. This created a more informed public and more connected society. The telephone took this further. With the telegraph, you needed to know Morse code or have an operator translate for you. With the telephone, you could just talk naturally. This made communication accessible to everyone, not just trained operators. By the 1920s, many homes in developed countries had telephones. You could call a friend or relative and have a conversation in real time, even if they were far away. Radio broadcasting, which started in the 1920s, created shared cultural experiences. Families would gather around the radio to listen to programs together. Everyone in a city or region might be listening to the same program at the same time. This created a sense of connection and shared culture that hadn't existed before. Radio brought music, news, and entertainment into homes without any wires at all. All of these communication technologies depend on electricity. The telegraph uses electrical pulses through wires. The telephone converts sound to electrical signals and back. Radio uses electricity to generate electromagnetic waves that travel through the air. Without understanding electricity, none of this would be possible. Let's also talk about how electricity enabled modern medicine. Hospitals today are completely dependent on electrical equipment. X-ray machines use high-voltage electricity to generate X-rays, allowing doctors to see inside the body without surgery. Heart monitors use electrical sensors to detect the heart's electrical signals. Ventilators use electric pumps to help people breathe. Surgical lights, sterilization equipment, refrigeration for medicines and vaccines, all electric. Electricity also enabled new medical treatments. Electroshock therapy, though controversial, has been used to treat severe depression. Pacemakers use small electrical pulses to regulate heartbeats. Deep brain stimulation uses electrical signals to treat Parkinson's disease and other neurological conditions. None of this would be possible without electricity and our understanding of how it affects the body. Transportation has been transformed by electricity too. Electric trains and streetcars appeared in the late 1800s and early 1900s. Today, many cities have electric metro systems moving millions of people daily. Electric cars are becoming common, promising to replace gasoline vehicles. Electric ships and even electric airplanes are being developed. The advantage of electric motors is they're incredibly efficient. A gasoline engine converts only about 20 to 30% of the fuel's energy into motion. The rest is lost as heat. An electric motor converts over 90% of electrical energy into motion. This is why electric vehicles can go farther on equivalent energy. They're just much better at using the energy they have. Now let's talk about computers in more depth, because they represent one of the most important uses of electricity in modern times. Early computers in the 1940s were massive machines filling entire rooms. They used thousands of vacuum tubes, which were electrical devices that could switch on and off. These computers could do calculations much faster than humans, but they were slow by modern standards, expensive, and broke down frequently because vacuum tubes would burn out. The invention of the transistor in 1947 changed everything. A transistor is a tiny electrical switch made from semiconductor materials like silicon. Transistors could do the same job as vacuum tubes, but were smaller, more reliable, used less power, and didn't generate as much heat. Within a few years, transistors started replacing vacuum tubes in computers. Then, in the 1960s, engineers figured out how to make integrated circuits, putting many transistors onto a single chip of silicon. The first chips had just a few dozen transistors. Today's computer chips have billions of transistors, each one a tiny electrical switch. These switches turn on and off millions or billions of times per second, processing information. Everything a computer does is based on controlling electricity. When you type a letter, you're triggering electrical signals. When the computer stores data, it's representing information as patterns of electrical charges. When the processor calculates something, it's routing electrical signals through billions of switches in specific patterns. When the screen displays an image, it's using electricity to light up millions of tiny pixels. The internet is also fundamentally about when you send an email or visit a website, your computer converts the information into electrical signals. These signals travel through wires or as radio waves to other computers. Those computers process the signals and send back responses. Data centers storing the internet's information are warehouses full of computers, all running on electricity, all generating so much heat from electrical use that they need massive cooling systems. This brings up an important modern concern. We use so much electricity now that generating it has become a major environmental issue. Most electricity globally still comes from burning fossil fuels like coal, oil, and natural gas. Burning these releases carbon dioxide, which contributes to climate change. We need the electricity to run our modern civilization, but we also need to find cleaner ways to generate it. This is why there's huge interest in renewable energy sources. Solar panels convert sunlight directly into electricity using a photovoltaic effect. Wind turbines use wind to spin generators. Hydroelectric dams use falling water. All of these generate electricity without burning fossil fuels. Nuclear power plants split atoms to create heat that makes steam to spin generators. and they don't produce carbon dioxide, though they have other challenges like dealing with radioactive waste. Scientists are also researching ways to store electricity better. Batteries have improved tremendously since Volta's time. Modern lithium-ion batteries can store lots of energy in small spaces. This is what makes smartphones and laptops and electric cars possible. But we need even better batteries to store energy from renewable sources, which don't produce electricity constantly. The sun doesn't always shine, the wind doesn't always blow, but we need electricity all the time. So the story of electricity isn't finished. We're still discovering new things and finding new applications. Scientists are researching superconductors, materials that conduct electricity with zero resistance. Regular wires lose some energy as heat because of electrical resistance. Superconductors don't, but they only work at very cold temperatures. If we could find materials that superconduct at room temperature, it would revolutionize how we use electricity. We're also learning to use electricity in more sophisticated ways. Quantum computers use quantum properties of electrons to process information in ways regular computers can't. We're developing better ways to wireless transmit power so devices don't need to be plugged in. We're using electricity to create new materials, to purify water, to grow food indoors, to power robots and drones. Each generation finds new uses for electricity because it's so fundamental and versatile. It's a form of energy that can be converted to almost any other form. Electricity to light, electricity to heat, electricity to motion, electricity to sound, electricity to sound, electricity to chemical reactions. This versatility is why it's become central to civilization. Looking back at the full story, from ancient Greeks rubbing amber to modern smartphones and electric grids, what have we learned? We've learned that nature has rules, consistent rules that we can discover through careful observation and experimentation. We've learned that patient, systematic investigation pays off. The people who discovered electricity didn't do it quickly. They spent years, decades, lifetimes studying and experimenting. We've learned that knowledge builds on itself. Each discovery made the next discovery possible. Gilbert's work enabled Franklin's experiments. Volta's battery enabled Faraday's discoveries. Faraday's discoveries enabled electric generators and motors. Thomson's discovery of electrons explained what everyone before him had been observing. Maxwell's equations unified everything into one mathematical framework. He learned that practical applications often come long after the basic science. The ancient Greeks noticed static electricity, but it took 2,000 years before anyone could use electricity for anything practical. This shows why basic research matters. We need people asking questions and doing experiments even when there's no obvious immediate use, because you never know which discovery will eventually transform the world. We've also learned that technology changes society in unexpected ways. When Franklin invented the lightning rod, he just wanted to protect buildings. He probably didn't imagine how electricity would light up cities, power industries, and enable instant global communication. When Faraday discovered electromagnetic induction, he couldn't have predicted power grids and electric cars. When Thomson discovered electrons, he couldn't have imagined computers and the internet. Discoveries have consequences that spread far beyond their initial purpose. Finally, we've learned that there's always more to discover. We know a lot about electricity now, but we don't know everything. There are still questions about how to generate it cleanly, store it efficiently, and use it sustainably. There are phenomena we still don't fully understand, and there are probably applications we haven't even thought of yet. The story of electricity shows human beings at our best. Curious, persistent, collaborative, creative, people from different countries and centuries working on the same problems, building on each other's discoveries, slowly revealing the hidden rules of nature. Not for glory or money, though some got those things, but because they wanted to understand, because they saw something interesting and couldn't let it go until they figured it out. That's the real story of how electricity was discovered. It's not just about the facts and dates and names. It's about the human drive to understand our world, to ask why things happen and how they work, to observe carefully, experiment systematically, and think creatively, to take something invisible and mysterious and turn it into something we can harness and use to improve lives. Every time you turn on a light or charge your phone or use any electrical device, you're benefiting from centuries of work by countless people. People who wondered why amber attracted feathers, who experimented with batteries and magnets, who risked their lives flying kites in storms, who spent years trying to make light bulbs that wouldn't burn out. who calculated equations describing invisible fields, who discovered the electron and revealed what electricity truly is. These weren't superhumans or geniuses beyond our understanding. Were people like us who got curious about something and pursued that curiosity. They made mistakes. They had wrong ideas. They argued with each other. But they kept at it. They kept asking questions and doing experiments, and gradually, piece by piece, they figured it out. And here's something to think about. Right now, at this moment, there are things happening all around you that you don't understand. Forces at work. Processes occurring. Phenomena you can observe but can't explain. Maybe in 100 years, people will look back and wonder how we lived without understanding those things. Just like we wonder how people lived without understanding electricity. That's the power of the scientific method and human ingenuity. That's how we went from ignorance to understanding, from darkness to light, from helplessness against nature to the ability to harness its fundamental forces. And that's the story of how electricity was discovered.